everybody here. Welcome to GOTO Amsterdam. Actually, this is my first GOTO Amsterdam, but I have been to Denmark for more than a decade. I welcome you to this talk, Architecture in the Age of Things. Unfortunately, it is not us two. So this talk is a joint talk by me and Gregor Hoppe, who unfortunately cannot be here today, so I'm two people. The gentleman on the left, well, not on the very left, but almost the left, this is me. But this is our host, Eddie, a member of our family. And there's Gregor in the Bay Area. So he's back with Google in Singapore now, and we did this talk together. Oops. As said, you can ask questions through the apps, but you can also shout at me. No problem, I'm happy to answer them. Perhaps not immediately, but we will take them and discuss them. Yeah, I'm talking about the Internet of Things, and I'll start with this quotation by William Gibson. It's already here, but just not evenly distributed yet. Yeah, and if we go there, I did a quick check. We know smartphones, we know smart watches, but everything, even dumb things like light bulbs, become smart. Our home automation, shoes become smart. It's not just Under Armour, but also Adidas and others, they have smart shoes, they're connected. The car is becoming smart. I don't want to speak about autonomous driving, because that's yet another discussion, but it is connected. It knows everything about you. So these are things you might know. Here are some examples from Allianz, an insurance company with whom Gregor worked prior to returning to Google. And they have automotive telematics, pay as how you drive, or claim prevention. They observe you, the insurance company monitors your driving style. Big brother is watching you. And if you go into the industries that I'm representing, also everything becomes intelligent. Remote control and service, travel management, passenger services, our turbines, they produce tons of data. They have local intelligence. They talk to one another on a peer-to-peer level. So we are already there, and the Internet of Things is pervasive within things we don't know, all of them. So it is already there. And there are a couple of tipping points that help making it so pervasive. And there are software and hardware things like very cheap sensors, the connectivity and the bandwidth. We have increased battery power. So we have smart sensors out there in buildings that are connected, that talk to one another, and they have a battery life of 10 to 15 years without service. So there are lots of tipping points. Also the user acceptance. If I look to my almost 16-year-old daughter, this is an adventure by itself, right? If you have kids in that age, especially girls, you know what I mean. But she is always connected. And she can live well without a car, but not without her smartphone. And we recently upgraded her high-speed data volume to a flat rate, right? Because she wants to stay connected. So there are lots of tipping points that made it affordable to build the Internet of Things. Yeah, I like this cartoon, so we can come to some little more details. There's one thing that I find very interesting when I talk to people in my environment. We want to be in control. But the question to you is, do you really think you can control the Internet of Things? And this is a more conservative estimation of what is going to happen. With 4+ billion connected people, 25+ billion connected systems, and 50+ trillion gigabyte of data in 2020. So there are other numbers by Cisco that are even higher. But this is a huge thing. And actually there was a study I can really recommend you to read. It is from 2004. It is a book which is available on PDF, free for download, on ultra large scale systems. Systems that are so big that they go far beyond the size of everything we know in scale. Yeah? So the code, the users, the data, the connections. But there are some properties that I think are very important when it comes down to how to design for the Internet of Things. One thing I like very much that affects us in industry is failure is the norm. You cannot assume something is correct. Something is broken. And you don't want your critical infrastructure shutting down just because something is broken. Huh? Continuous evolution and deployment. Everything is in flux. Inconsistency is part of the game. So a lot of things, let's say traditional software engineering tries to eliminate by lots of careful design, architecture requirements, engineering, and here we have the big mess, and we have to deal with this. So I go a little into that from a high-level view, and this is a picture from the Apollo taken by Apollo a couple of years ago, by the last Apollo flight. I took this intentionally because I had the pleasure a couple of weeks ago to listen to Margaret Hamilton. Who of you know Margaret Hamilton? Oh, well, she coined the term software engineer, and she was actually responsible for the Apollo flight software. And she told us how they debugged. Yeah, they had this drive, and if you need another hole, you took a pencil. Or if some bug was there, you took some strip, and yeah, so this is how they looked on the systems, and that was an amazing talk. And she ran into a lot of problems many years ago, decades ago, that are now coming up again. So this is a very super high level view of kind of architecture. Architecture is somewhat of blocks that are connected, and if you browse the literature, especially reference architectures about the industrial internet or the Internet of Things, you find the cloud space with lots of data analytics and operations apps, and above that are the business apps. Then there is the edge. Well, that in traditional perspectives on the Internet of Things were, let's say, just data sources. But with the increased compute power and networking power that we have on the edge, well, intelligence is more pushed into the edge. The things become more intelligent. And that is one trend that we see, and you see this also, you can read about those trends in lots of articles. One of the big trends is edge computing. So we have this pendulum that from the data center to the PC, then the cloud, and now it swings back to the edge. Edges become more intelligent, but also the things that are connected by edges, by edge devices are becoming more intelligent, so smart sensors, intelligent actors. So these kinds of things become available because we have more compute power in the things. And in between are the gateways that connect the two worlds, but also have sufficient computational power to run, let's say, applications that connect multiple things and represent them to the cloud world. In many of the architecture sketches, you find the traditional way of data flows up and control flow goes down to the edge. That was true, or that is true for the, let's say, most of the architectures in the Internet of Things. But if we have let's say, an autonomous car, an intelligent thing, a cobot, A robot that is working with you, hand in hand. Then these things have intelligence, and because the compute power on the device may not be sufficient to run, let's say, long-running data analytics computations, well, there is also the idea that we have services in the cloud that control a fleet, but belong to one thing. My prediction, should I behave in the future? So that changes a little bit data and control flow direction, so it is bidirectional, so we have data flowing in both directions now and control also flowing in both directions now. So things invoke cloud-based services on their behalf. They control them. So this is the sketch, and what I find very interesting when I talk with Gregor about the different interests that different parties have in the Internet of Things. They are the industry versus the consumer interests. So, and I go into, as I'm obviously representing industry here, I can play that game a little better than the other. But I will try my very best to tell what Gregor had told the audience. But in the industry, we run things that run safety-critical software. A train. Do you feel well on the train? When do you feel well on the train? It's running with 300 kilometers per hour, and yeah, well, you want the software to be safe. Now you have a continuous deployment. Oh, I'm updating the control system while running. You don't want the train to be stopped, and but you want to preserve the operational quality. So also the connectivity, reliable, high quality connectivity. If two robots cooperate with one another, if they collaborate, high precision welding, well, that requires reliable quality of service in the network. And on the cloud level, you want to manage all those infrastructure systems. On the consumer side, it's more about how can my day-to-day quality of life become better? We want to use the Internet of Things to our service. We want to be informed about the state of our home, the content of our fridge, whatever. We want to be connected to have access to information, and we use the cloud in the background to improve the breadth and depth of our experience. Well, we had in this keynote this morning, we talked a little about the price we pay for that, but that's another question. But these are conflicting interests, and if you go back to what I said before about the ultra-large-scale systems, there are these conflicting requirements. And if you go to the technical side, you can also see there are a lot of high reliable in-field control and operations requirements like low power, low latency, hardcore real time. So if you are in the machine tool domain, CNC machines, then we run in 50 microsecond cycles from sense to act. And if two machines connect to one another, that doesn't extend the cycle. Latency is the physical processes drive what is required, because the physical processes don't stop when your software is not fast enough, when the software fails. Whereas in the consumer world, we want affordable and stylish smart things. My daughter is the best example. She looks onto functionality, but also whether this is stylish, whether she is in. Users don't want to spend much money and want usable, valuable ads. So these are the requirements there, and how can we achieve them? Looking on the baseline architecture, I want to go into a couple of things that I find very essential. Of course, we need to touch microservices. And the point is that one thing I find very important is that there is a big question of where do we want to allocate our application logic? And that depends on a lot of things, like how close to the physical process or to the thing we want to be because of latency, real time, safety critical things, autonomy. And on the other hand is how complex is processing. Like, are we operating of terabytes and petabytes of data? Do we have deep learning? Do we have long-running computational actions and so on? So this depends. So this is one thing. Big decision, where do we put our application logic? But for some things, there is a continuum. There are applications that you can deploy very close on the things on the edge, but also in the cloud. And it depends on the concrete solution, on the concrete system, on customer preferences. So in our domains where I'm involved in, factory and process automation, customers are very, let's say, they're very skeptical about the cloud. And if at all, it is only the big customers who run their own data centers. Most companies want to have things on premise. There is a person on the shop floor who is responsible for the safe production, and that guy doesn't trust the cloud. There is this, these guys want to be in control. Whereas as a small and medium enterprise company who just enters the market, a startup, well, they don't have the money to invest into all that infrastructure. So they say, well, for me it is important to be in business fast. So just give me the service. So and that has some constraints on how you design and deploy and connect and orchestrate your applications. Yeah, microservices, I don't want to go into depth into that with one exception. This has been advocated since a couple of years, and these are some famous diagrams you probably know. We want to go from the monolith to something that is decoupled. Each feature is a product by its own, with its own life cycle, and connected by a dump pipe messaging. So on that allows independent teams to build them, to test them, to release them, to deploy them, and to bring them into the Internet of Things, because otherwise you cannot handle the huge size and also the ever-changing requirements in you cannot handle them at all. Oops. Okay, so this is another picture you probably know. And the microservices are, to me, important because they are one of the key enablers for deployment flexibility. Yeah? It is not just the modularization that they advocate, but if you design them right, you can deploy them where you think it is most appropriate. And you can change this throughout the life cycle of your application, throughout the life cycle of the system. For example, we have in our industry architectures, we prefer, let's say, going to the edge as far as possible, making the edge smart. But these are devices, despite all computational power of today, they may be overloaded. So then we have, well, either pre-installed on, let's say, on a gateway, or more on-premise server, or on the cloud, another instance of those services, and then we shift load around, and we uninstall those services on the one edge and move it to something else, to another device. So microservices are not just modularization and for modularization and enabling teams to build applications independently of other teams, but also to allow for the dynamics in the Internet of Things, where you want to push, deploy your functionality, where you want to run it. On the other hand, I like this quotation by Simon Brown, and I'm often involved in religious debates about microservices. I like this quote because from a design perspective, what is the difference between a well-designed microservice architecture and a well-structured classical SOA monolith? Nothing. You have to think about how micro are your services? What is the scope? What is the responsibility of each service? How do they interact? How do they orchestrate to an entire system? It is the same set of questions you have to answer and you have to design. And Simon concluded so, and this begs the question, and that is one of the big problems I see, that if you can't build a well-structured monolith, what makes you think microservices is the solution? Just saying all my problems are resolved because I go microservices doesn't help you build working systems. So this is one of my favorite quotes, and this is actually the only slide that I added to the original talk over the other ones. If you have so many microservices or apps, whatever, systems of systems, how do you communicate? And there's this, this is the part where Gregor is very pushy on this, is asynchrony. He doesn't want applications to be synchronous because that increases the coupling, that maximizes, let's say, failure because you depend on something else. So asynchrony is the key to resilience because in an Internet of Systems, there are lots of obstacles. It's not just about the coupling and dependencies between microservices or applications, but the communications may be slow and unreliable. What do you do then? Yeah? And the error handling we can handle much better. And he goes into, you know this from him, from his famous integration patterns book where he did all this messaging stuff. So there are a lot of communication patterns based on eventing and messaging that help you build asynchronous communication. And if you design for the Internet of Things, make sure your applications talk to one another in an asynchronous way, that they can handle communication failure, that they don't block if something is not available, and so on and so forth. So these are things that are very important, and that may sound easy in the first place, but if you have a system, we built this, where about 500, 600, 700 microservices are talking to one another in an asynchronous, event-driven fashion, and you still want to have a deterministic, predictable behavior, that is a challenge. Especially with respect to reliability, with respect to certification, and so on and so forth. So there is, on the other hand, there is no way around asynchrony, but it requires some experience to get this right on an application level. I'm not talking about one service talks to one other service, but on an application level. This can become very challenging. And it is if I look on systems, specifically microservice-based systems, where my territory as an architect is, I trust the teams to build their services well. I'm designing between the microservices. How are they orchestrated? How do they communicate with one another? What if something fails? So this is my territory, and that is also why this is perhaps more architecture relevant than it was before. We have events and event streaming. So these are, let's say, other things in asynchronous communication, data. Yeah? We have lots of data available. Our smart things produce a lot of data, and we want to stream them to where they are processed. Event-driven communication pops up. So these are kinds of things in the, let's say, architect's toolbox to connect all the applications to a system. I said I want to strive for deployment flexibility. On the other hand, there is a huge universe of different execution platforms around there. Especially in brownfield. Yeah? We have devices out there that are there for 20 years, 25 years, and all of our customers ask for how can we get them smart, how we can get the Internet of Things to our factories, to our plants, or whatever. So there are some techniques by this, but the downside is you have all this heritage of operating systems, programming platforms. There is no such thing like a homogeneous programming platform like the iOS or something. And that goes then, two technologies come into place, like virtualization and containerizations. They have pros and cons. For example, virtualization we primarily use to package existing applications and push them to that environment where we want to execute them. Primarily big applications into the cloud. You may know about the lift and shift strategy. That is, you take the existing application as is, virtualize it, lift it to the cloud, and then begin to partition it and make it nice in terms of a microservice architecture. But the idea to the customers is to have a cloud offering that looks like as a service, but in reality it is not a multi-tenant application, it is per user, and you have desktop as a service, it mimics the software as a service. You as a vendor operator, you have higher OPEX because you do not scale with multi-tenancy, but the customer has the impression that they get software as a service. So this is so for heavy lifting of legacy applications, we use virtualization, and for the newer approaches, we go with containerization. There are multiple approaches, Docker, Rocket, but the most interesting trend we are looking at everywhere is Kubernetes, because let's say containers are, let's say, a mechanism, but Kubernetes and this entire universe is for orchestrating the applications. This is kind of the conductor of the Internet of Things, and this is really crazy what's going up there. And I'm also wondering what container technology will be the most predominant in 5 years from now or 16 years now. Will it be Docker or will it be something driven by Kubernetes? So watch out. There's still, despite the fact that Docker is, let's say, the big name, the big kid on the block, there might be others in the future. But in terms of managing the Internet of Things, containers are not sufficient. The other one is the runtime. We had a lot of debates on, especially in our environment, can we just assume there is some whatever operating system and we deploy the containerized apps and microservices down to that. That is not entirely possible in some domains, and therefore we came up with an idea, I don't want to say reference architecture, but a kind of sketch of how, at least in industrial environment, we consider a runtime that allows for flexible deployment of functionality across the continuum from cloud to edge. And in industry, I think we had this talk about IT security and network. If you run a factory network, you don't want to open it to everybody. And that is why we thought, well, we have a kind of, for the device, a kind of built-in infrastructure. What is not on the picture, it's also containerized, so we can exchange the modules there as well. I left that out and only showed containers for the applications and apps, but the services that help keeping control over the physical resources that we address with our apps. And that is not just also for security, it's also a safety net for programmers, right? If you are an app developer and you now deploy this to the running factory, the production of cars, you don't want to stop that production. Yeah? And you can test as much as you want in your virtual environments, in the cloud, in the pre-production environment. On the device, there's some operator who pressed a button that changed the configuration setting and nothing works. Or because in the machinery that happened to us, we do real-time microservices, control services. Things didn't work because some hardware was exchanged. There was one filter exchanged by another one, and that had implications on the latency of applications. A hardware change. You may not notice all this. And therefore, keeping the, let's say, the resources that connect the runtime with the physical environment a little bit more protected, that is one of the considerations that we have in architecture. You may choose a different way and move those services either out or up to the application level. It depends on how open you want to be and what are the consequences of failure. But in the end, you have a lot of those things here in your runtime, in your containerized runtimes, and then you can, this allows great flexibility for deploying functionality. One thing is important though, you are not walking alone. The Internet of Things only works in an ecosystem. You are not the only vendor, you are not in control. Many parties have cool ideas and you want to let them participate in the progress. And that is why all those environments, all those runtime infrastructure must be ecosystem friendly. This is easy in the cloud, you are familiar with this, but it's not so easy if your target environment is a device in a factory. Then you have to do a lot of things to make it more open for the ecosystem and DevOps. For example, if you deploy, then we have tests in pre-production to check whether everything works fine. Then we switch over to the new version. Then we run tests in production to see what happens when these services are live. Have lots of recovery and resilience features built in to handle that if something fails. But if you are not open, you will not succeed. If you open too much, you may fail. It's a kind of, I thought whether this is a new, let's say, setting for the open-close principle that Bertrand Maillet once brought up. But these are considerations about runtimes. It's more than just pushing containers on plain Linux. That is an architecture message here. You need to design what infrastructure services you want to have and you need for your things and how open you want to make them, depending on preferences and requirements. Oops. There are other options, and you can get all of this out of the box, and we have a talk here that is why I'm not going into much detail here about Amazon Greengrass. It's today or tomorrow? Today. And this is another approach. There is, what you say, one platform that spans cloud and edge. Let's more or less in a nutshell. Serverless computing. And that is another way. But this is only possible in a very homogeneous environment, which is, let's say, just a small portion of the Internet of Things. Where this is possible with one technology. The reality is we have a polyglot technology and then we have all the other approaches. But if you are in a homogeneous environment, if you have a chance to build your Internet of Things, I don't want to say from scratch, but you have technology in your hand, then it is actually an option to get everything out of the box. Microsoft is working on that as well, so Amazon is not the only vendor. This is just a, let's say, eye-catcher for those types of technology. But then you are bound to a particular environment that may require a lot of invest into porting applications and, well, the diversity of the real world is not fully addressed here. But it depends. If I go to the cloud, I don't want to go into how to design operations and business applications. But the data analytics, I think, is let's say, the biggest thing that the Internet of Things brought to us in cloud computing. The availability of massive amount of data and the computational power to process them. And how to process them. And who of you knows about the Lambda architecture? Oh, not too many. Oh, this is originally designed by Nathan Mas for Twitter, and this is the, let's say, the archetype of data processing architectures. We have a batch layer for processing batch data or historical data based on the MapReduce idea, and then we have streaming for the speed layer for real-time data processing, and then we have a serving layer that offers different views onto those data. And despite the critiques and variations, if you look at well-designed big data processing systems, they more or less follow one of the flavors of the Lambda architecture. I can recommend you reading the book. So there's a book, I think, by O'Reilly about the Lambda architecture. This is the architecture thinking of big data processing in a nutshell. Yeah, MapReduce, publish, subscribe, observer, command processor, command, parallel pipes and filters. These are the architecture patterns underlying the Lambda architecture. And the nice thing is that for each of those layers, I go into the batch and speed layers, there are lots of technologies available, like Hadoop. You can do the MapReduce part very nicely, out of the box. Yeah? This is not something you need to program. Likewise, parallel pipes and filters. Twitter Storm was the original technology, and then it went public, open source. But there are other technologies available there as well, so that help you designing very flexible streaming pipes for real-time data processing. And this is just a not representative overview of available technologies. So the nice thing is you can choose a lot of technologies, but when you compose them, be aware that they have underlying the idea of the Lambda architecture or a particular layer that you're building. And you are most efficient in building up if you follow these architecture ideas. It's not just about the technology, it's also about the ideas, the architecture and design ideas those technologies are following that are important. But you don't need to program that by yourself, right? It will take too much time. So this is also my message. Take the technologies as an architect. You need to be familiar with at least the most important ones and have experts know all the details of each technology. But from an architecture perspective, it is the Lambda architecture that drives you. Coming to the gateway. Yeah, the original design, the original purpose was to bridge networks from A to B, the gateway. But there's another term. Between cloud and the edge is the fog. Who of you heard the term fog computing? Heard, yeah. Well, coined by Cisco, of course. They have the routers, and these are machines with massive computational power. And they said, why don't we bring the cloud to the edge or near the edge? And if the cloud is a weather phenomenon, when the cloud comes down to the ground, it is the fog. Hence the term fog computing. So the gateways can offer, let's say, great opportunities to make dumb things more intelligent. So if your thing is really dumb, you may have a software representative on a device near to that thing that represents the intelligence of the thing. And the gateway is one of the natural places for doing so. And the other thing is that there might be computational resources like analytics, like storage, like handling state that goes beyond one thing. And these are common services for all the things that are connected to the gateway, so that the intelligence goes to the field. So this is actually, I recommend you to look at how you can utilize the compute power of gateway and the increasing computational power of edge devices for distributing your application functionality, your intelligence across the Internet of Things infrastructure, across the cloud to edge continuum. Yeah, and that is called fog computing. You find this symbol quite often if you search for icons to make dumb things more intelligent. Yeah, I like this photo. The edge. Yeah, there are different types of edges, like a motor, or a smartwatch, or a temperature sensor, and they, of course, have different requirements. This is also an edge device, and it's a thing of things, actually. Right? We have the train with the control controllers, the panels in the car, we have a drive system, a brake system, an energy system, a door system, whatever, and this is a connected thing. And the key thing is we have to change our way of looking on it. What if something fails? Traditionally, if you let's say, have a failure on your smartphone, one person is annoyed and many others don't care. And, well, is the provider caring for you? Retry, restart, you know this. In systems, I'm representing fail-safe with the usual option. If something goes wrong, all signals go to red, everything stands still. That is doable, but this is very expensive, and it's a no-op in lots of processes. Yeah? You cannot go to a safe state while the aircraft is flying. Yeah? You want to roll forward, you want to fail operational. And that is what I said earlier, failure of things is the norm. Safe state would result in stepwise global shutdown. There are lots of articles. What would happen if our power network gradually fails? If there's a failure and it is not fail operational, we will have no power within an hour across the globe. And this is something we need to design into our apps. The closer we go to the things, at least if they're controlled to more than just smartphones or things, but things in a, let's say, industrial world, like this building, for example, you want resilience and robustness, and you need to design for that. You need to handle all those things. I like a quotation of one of our chief architects for distributed control systems. They control chemical plants and so on. He said, okay, if a feature or a microservice fails, I want a system that has one feature less than before, but I don't want to have a dysfunctional system. And that you have to design into your applications, that you can deal with such cases. IT security. Well, this is something that is very important. We addressed this here with several talks. We had one this morning in the keynote. We have some other things in the afternoon. But you need a security concept that allows you to build more complex things from small things. And an atomic IT security architecture that pairs all the known technologies. With respect to safety, well, there's a lot of research going on of how to address safety in such applications, but for the moment, the trend is keep safety critical things entirely separated of uncritical things, and do not connect them too much to the Internet of Things. A lot of architectures are designed that way, that they don't touch safety yet, I would say. But keep that in mind if your application is somewhere in the context of safety. Networks. Yeah, lots of protocols. MQTT, easy to use, widespread. There are lots of alternatives. You probably know this. We use that a lot. But if quality of service comes into the game, then I suggest you take a look at time-sensitive networking. This is an IEEE set of standards where you have more control over things like timing and synchronization. You have path control and reservation, a lot of things for ensuring quality of service. So that is heavily used in industry. But what I want to tell you is there is a huge set of protocols available, and the nice thing about standards, all standardized, is that they have so many to choose from. That is a famous quote by Andrew Tannenbaum on operating systems, but this is also true for networking. I skip over all those network topologies. Semantics. If we want to have smart things, we need semantics, not just data. And industry is OPC UA, a standard, and they are enhancing it to make it fit for the industrial Internet of Things with a lot of profiles that address semantics, but also the OWL, Web Ontology Language, is a way you can add semantics onto the data. The key is smart data and not just raw data, right? And the semantics allow you that things can interact with one another. So keep that in mind when you design your communication, semantics. With respect to quality of service, software-defined network is a kind of, we virtualize computer resources on a machine, and software-defined networking virtualizes your physical network. You have lots of task-oriented virtual networks with dedicated resources, with guaranteed quality of service, so that you can do a task between a communication between a set of things without interfering the communication of other things. And they are entirely separate. And this is the trend in networking for, you can have topologies like distributed, hybrid, and centralized control. We are playing a lot with this standard. Together with the time-sensitive networking, we find this a very cool combination of getting quality of service into the network on a task-driven basis. We can do this dynamically, this virtualization. Right. Coming to the end, the architect, I recently watched this scene. This is brilliant. Yeah, it's brilliant. And the way this guy talked with the fascination of the mathematical equations. Right. So, what is important? If you are designing or dealing with the design of apps in an Internet of Things, or from a systemic perspective responsible, then think you are not in control. These are beyond your control, so give up your control. Think distributed, think concurrent, messaging, events. Remember, things will always be broken. Decide about, you have to think full stack, from sensors, protocols, processors, in the edge to cloud continuum. And we heard this morning, this goes pretty much beyond technology. Yeah? Privacy, liability. DevOps is important. We have 2 tracks here on the conference, so I don't touch that. But think there's nothing stable. Everything changes. We want the feedback loop, back to dev, what works and what doesn't work. So these kinds of thinking is evident if you design for either an app or an entire system. But on the other hand, I was wondering, I think the true challenges of us that we have to face are cultural. It's not just to give up control, but I don't think we are users of the Internet of Things. We are things in the Internet of Things. Just watch how carefully you care for your compute device. You clean it, you connect it to power, yeah? Think about how much you are controlled by the Internet of Things. And I think it is our responsibility as software developers to make the Internet of Things a place that is worth to live in. And that is beyond architecture and technology, designed for something that is good for everybody, for the society here. Because otherwise, well, you can do a lot of bad things with this. We don't want to see. Right, so that was the end. Thank you very much.
Thank you.